So with this video, we're at our third lesson for Chapter 3. It's our chapter where we're working on just finding derivatives quickly. And today we're going to focus on physics and how you can actually see the calculus world and the physics world kind of interconnected together. So off the start, we're just going to spend a page here and just kind of set up some raw content, just some theory, and then we'll go and apply that to an example over the next few pages. So first thing, in calculus, we often don't like to use the letter d like we would in physics because we have d from the Leibniz notation for derivatives. So if you want to talk about just the position of an object, where it is, the best variable for us to use in calculus is often s. So I don't know why we chose s, but s is actually going to be the position, and it's going to tell you where the object is. It could be in meters, maybe in feet, at any time t. If people ask you for the displacement of an object, what they're actually asking for is the change in position. How much has the position moved around over some sort of time interval? And so if you're calculating that using your position function, you'd be trying to look for the change in s, right? You want to know how much that's changed. And so you'd be taking the position at some second time and then subtracting the position at some first time. That'll tell you the displacement. If you want to know the average velocity, that's going to occur over some time interval. The way we can express that is put a little v there with a bar on top, and that says, yeah, we're going to be doing some sort of averaging here. So this is going to be the slope of your position graph, but this is going to be an average slope, an average rate of change. So I'm just going to put that in here. This is just an average rate of change. So whenever you see that phrase, rate of change, we're always just thinking, okay, slope. So average slope of position. So we take that position graph, that graph S versus T, and we're just going to find a slope on it. So the calculations would actually be something like this. How much did the position change divided by how much time actually changed? So you're going to be taking your change in position, well, I guess the displacement, right, if you think about it. And then we're going to take that displacement and divide by how much time went by, t2 minus t1. Now, if you want to do an instantaneous assessment of how fast something is going, we could call that the instantaneous velocity. And it's going to be the, not average rate of change, but the instantaneous rate of change, otherwise known as derivatives, right? So instantaneous rate of change of position. That'll tell you the velocity at one given instant. You know, another way you can think about this is the slope, the tangent line. At least the tangent line on the position graph. So how can we denote that in our calculus world? Well, we could just say, yeah, that's the velocity at any given moment, and at different times it'll have different values, so it's a function of time, and it really is just a derivative. So if you were Newton, you would just say, yeah, that's s prime of t. Or if you're Leibniz, you would say, well, I'd like to actually explicitly show that I'm doing a derivative with time, and he would say, oh, that's ds dt, right? Good old calculus doing that instantaneous slope calculation. Okay, well, let's do the last two rows again, but let's bump up to the next quantity that we've got in physics. Let's talk about acceleration. So if you want to talk about average acceleration, that's going to occur over some time interval. That's going to be, just like we said, average rate of change in position up here to get to velocity. Well, now we're going to do the average rate of change in velocity. So we're doing the slope, an average slope off of that velocity graph. Yeah, writing that down mathematically, we could say, oh, okay, look, we're looking for changes in v divided by changes in t. So we're going to take the velocity at some later time and then subtract off the velocity at some earlier time and then divide by exactly how much time has gone by, t2 minus t1. Okay, well, just like we did with the story with calculating instantaneous rates of change on position to get to velocity, instantaneous velocity, we can now do the same thing here. If you want instantaneous acceleration, the acceleration right now, that is going to be the instantaneous rate of change otherwise known as the derivative. But this is going to be the instantaneous rate of change in velocity. Or just to word that another way, if you can imagine a velocity graph, we're going to be doing the slope of a tangent line. Okay, off of that velocity graph. So slopes on a velocity graph, just generically are acceleration. We can do an average slope or we can do an instantaneous slope. Now, writing that down, we can say, okay, the acceleration, which varies with time, so it's a function of time, it is the derivative of velocity, so it's v prime of t. Or you could say, hey, look, v is just the derivative of s, so we have to go 2 derivatives down the road in order to get to acceleration. Or if you're Leibniz, you would say, hey, how about we call that dv dt? Or if you wish, 2 derivatives of s, both times with respect to t. d squared s dt squared would be how we would say that. Now, last little bit of just content here on this page. Let's just talk about kind of translating English phrases and words, into calculus. If somebody says to you, oh, hey, that object is moving backwards, or maybe they ask you, is that object moving backwards? What do we do in order to translate that into our kind of math world? Well, if you're going backwards, then you've got a negative velocity. So s prime, this is the same thing as velocity, right? So s prime would have to be less than 0. It would have to be negative. Then you would know, oh, the object's actually moving backwards. So those ideas are interchangeable, right? A negative velocity means the object is moving backwards. If at one little moment in time, the velocity happens to be 0, then the object is stopped. Now, it may not be stopped for long. It could be like a car at a light that's just turned green, and they've hit the gas, and they're going to accelerate away, but right now, at this instant, they might not be moving yet. Okay, the opposite of moving backwards, if we've got a positive velocity, if s prime is bigger than 0, then you can say, oh yeah, this thing is moving forward. And if you're ever asked to justify, like, hey, at what time is something moving forward? And you say, well, it's at these times, and then they say, justify your answer. You must comment on that column over on the left. You have to say, well, look, the s prime is positive here, so that's how I know this thing is moving forward. Okay, let's take those same ideas. Let's bump up now, though, to talk about acceleration. So this s double prime for the next 3 rows, now we're talking about acceleration. If your acceleration value is less than 0, then the phrase we would say is, oh, this thing is accelerating backwards. Be careful, you can be moving forward while accelerating backwards. You could be in a car traveling forward down the road, but then when you hit the brakes, you're still going forward for a while, but you're accelerating in a backwards direction. So those two things can be of different sign. One could be positive, one could be negative. If your acceleration is 0, then your object, at least at that moment, is moving at a constant velocity. And if your s double prime is greater than 0, if your acceleration is greater than 0, we could just say, oh, you're accelerating forwards. Now, we'll talk about a little issue farther down the road in the course, but I'm just going to mention it now. If the acceleration of an object is negative, that does not necessarily mean that it's decelerating. To be decelerating means that the acceleration and the velocity are of opposite signs. So if you're going forward and accelerating backwards, yes, we would say that's decelerating. But if you're going backwards and accelerating forwards, that's also decelerating. So just be a little bit careful with that little English phrase. Okay, let's try this out for a few pages here with just an example, a little physics story. We'll see how the world of calculus can deal with the physics. So we've got the story about an object that has a position function given by this polynomial here, this cubic polynomial. I should have probably been more clear about what the units are, so maybe I should have said, here's the position in whatever, feet or meters. Let's say it's meters. For 0 to 5 seconds. And so we've got this graph. It's already been drawn there, the cubic function for 5 seconds. Up and down, you can barely see the axis label there. I'm just going to make it a little larger. So this is S, measured in meters. And then our cross axis, also barely visible, that would be time, and that's going to be measured in seconds. And great, I've got this nice clear, graph of S versus T. Now, just maybe stating the obvious, but let's do it. This world of physics wants to talk about position and wants to talk about time, right? So we've got the S-axis, we've got the T-axis. That's our physics world. But I've got this graphing calculator, and I don't know about you, but my graphing calculator doesn't easily allow me to change the name of the axes. So I'm going to have to be, if I use my calculator, graphing Y and X, and I'll just have to understand that, oh yeah, okay, if I'm doing a physics story, that X and T, those are going to be the same thing, right? And Y can be my position. Okay, here we go, diving into the calculus now. First thing says, can we go and find the velocity just as any function of time? Absolutely. This is actually pretty easy to do because velocity at any time, it's just the derivative of position. So I just have to take a derivative of that polynomial. Now I'll just go term by term. The t cubed, well, that 3 comes down here, so 3t squared. Moving along, minus 6t squared. The 2 comes down, we're going to have minus 12t. And then the derivative of 9t, that linear term, is just going to turn into the constant 9. Okay, well, that was pretty easy to do. And now the next part says, can you go and find the acceleration as well? Yeah, sure. Acceleration at any time, that's just going to be a derivative of this velocity that we just found. Or another way to say it, it's going to be the second derivative of the position function that they gave me. So I just go and do one more derivative. The derivative of 3t squared is going to be 6t, and the derivative of that linear term minus 12, or minus 12t is going to be minus 12, and then the derivative of 9 is going to be 0. Okay, great. So we now have the ability to find the velocity or the acceleration at any moment. And here come a couple of those questions. First one says, can you go and find the initial velocity? Yeah, sure, absolutely. So what they're saying is, can you go and find the velocity at time is equal to 0? Right? That's all they mean by initial velocity. So super easy. We just have to go and substitute 0 in. Because this thing was ready for any time, well, we're going to go and put the initial time in of 0. And as we substitute that in, we'll have 3 times 0 squared minus 12 times, a lot of easy terms here, right? And then this 9 on the end. Yeah, okay, the velocity at time 0, often written just like this, v with a little 0, often pronounced v naught, kind of the British way of saying things. That's just going to be 9. And the units would be the slope off of a position time graph, so it would be meters per second. Same plan. They're saying, well, can you go and find the velocity at time 2? You know what? We can find the velocity at any time you want, right? We'll just go and take those times and drop them into this machine that we've got. So here we would go 3 times 2 squared, minus 12 times 2 plus a 9. And if I haven't made any mistakes, I think that velocity at time 2 is going to be a negative 3. Again, it would be the slope off of a position graph, so it's going to be meters per second for the units for that. It could be feet per second, right, if it's a story about the position being in feet. The next one, when is the object stopped? That's what they want to know. So they're kind of asking us, t is equal to what, right? What time of day does this happen? Well, here's what I know. I know this general equation for velocity. It spits velocities out at every time. 3t squared minus 12t plus 9. That works at every time for those 5 seconds that we're looking at. I'm wondering, hey, are you ever 0? Because remember, to say that something is stopped means that the velocity has to be 0. So yeah, okay, we've got this simple little equation to solve. We could do some factoring. This thing actually factors with a common 3, and then it goes t minus 1, t minus 3. You can check me if you want. I think that's right. And that would have to equal 0 if we want this thing to be stopped. So you ask yourself, well, could that ever happen? It's kind of like well, it's not kind of like, it is the 0 product rule. So you start looking at all the different factors. Well, maybe it's the 3. Nah, it's busy being 3. No answer there. Maybe it's this binomial. Oh yeah, okay, there is one answer there. Maybe t could be 1 second. That would cause that expression to equal 0. So there's one answer. And then the other binomial, could you be 0? Yeah, sure, if t was equal to 3. So I have these 2 moments when that object is actually not moving at all. It's not going forward or backward. It's just totally stopped. What is the object's acceleration at t equals 1? I have no idea. Let's go find out. Right? So I want to go find a at 1. I'm going to take that time they're giving me and just drop it into that machine I've got back in question B at the top of the page. 6 times t it said, so I'll go 6 times 1, that's the time they want, minus 12. Okay, it looks like the acceleration at time 1 is going to be a negative 6. Now, the units, you might know them from physics, but they are going to be the slope off of a velocity graph. And velocity was already meters per second. So if I go and do the slope from that, I'm going to have meters per second squared. Okay, so far so good. This thing seems to be falling apart pretty nicely. There are more questions just over on the next page here. Let's keep trying this out. When is the object moving forwards? Well, I'm going to tie that in with when is it stopped. I know that it stopped at time 0 and at time 1. So I'm going to look at it this way. Just kind of think of the timeline. I was going to say number line, but I guess it's a timeline. I know we begin the story at time 0 and we're supposed to stop at 5 for this question because they said so. And at time 1 and at time 3, this thing is stopped. So those moments there, time 1 and time 3, they kind of make like little cut points on the timeline, right? I don't know if I can draw scissors or not. Right, there we go. Yeah, I'm going to take my scissors and I'm going to go and cut my timeline. And it looks like time 1 and 3 are not times when it's moving forward, but maybe, maybe, I don't know, I've got to go check. Maybe this thing could be moving forward at this part of the timeline, maybe in here, and maybe in there. So let's check all of those in between times and just see what's going on. So I'm going to start off by checking that interval of time. And in fact, I'm going to use interval notation. Let's go from 0 to 1. And I'm not going to check 1 because I know it stopped there, but 0 is actually a valid spot when this thing is beginning. So anything in here. What I do is I just go and pick any time in there. This is one way to test it. Like, let's try a half, right? So you go and you check out the velocity at 0.5 seconds. And when I tried that out, I got positive 3.75 meters per second. So it's definitely moving forward at time 0.5. Now I know it's not going to stop until you get to time 1. So it's got to be moving forward at least up until time 1. So that's going to give me one part of the answer. All right, let's just keep checking. Let's do some more time intervals here. Let's go and check from 1 to 3. I don't want to actually check 1 or actually check 3 because I know it stopped then. But what about all of the times in between 1 and 3? So I'll just sample one of them. Like I'm thinking time 2. That could be good. And when I tried that out, I got negative 3 meters per second. And you might think, well, that was obvious. It was moving forwards in the first interval. So clearly it's going to move backwards now. Be careful. Sometimes it'll move forward, stop, and then move forward again. So you have to check each interval one at a time. That interval doesn't look successful. Okay, let's check out the last possibility. What about after 3, but up until and including 5? So you pick any time you want in there. 4 is a nice easy time to check. And when I tried that, I ended up getting 9 meters per second. So this is a moving forwards moment, and that's a moving forwards moment. So if people are saying, okay, well, what's your answer? When is it moving forwards? Then I would say, hey, this is my answer. From time beginning and including 0 all the way up to just before 1, and then after 3 all the way up to and including 5. Okay, those are my two answers when you're moving forward. And if you wanted to know when's it moving backward, from 1 to 3. Okay, H. What is the position of the ball when the velocity is 9 meters per second? So they're asking us to see if we can figure out where this thing is. Okay, where's the ball, right? This object. And they're not telling me a clear time. I have this nice position function that they gave me, but I need to figure out, well, what time does that happen at? So my first priority is to figure out, well, when does this actually occur? If you tell me or give me a chance to find out when it occurs, then I can tell you where it is. So when does that happen when the velocity is 9? Well, that would be when this velocity machine that we've made, 3t squared, we did this on the other page, minus 12t plus a 9 would have to equal 9. Okay, well, just solving, 3t squared minus 12t is equal to 0. Okay, we can do a little factoring here. We can extract a 3t. Then we would have t minus 4 is equal to 0. Okay, so I have the answer for when. It's going to have a velocity of 9, actually twice, at time 0, right off the start. Actually, we saw that on the previous page, right? It says, what's the initial velocity? It was 9. And also at time 4. Okay, well, now I know when this issue occurs. Now I can go and figure out where this thing is at. Because they're asking me, well, what's the position at that spot? I don't know. Let's go find out. So now we're going to answer the where question. So I guess what it comes down to is our position function is just beautifully arranged to tell you the position if you know the time, right? Like the machine was s of t was equal to t cubed minus 6t squared plus 9t. It works with t's, right? So you had to have the t's in order to know where this thing actually is. So I'm going to take those two times, 0 and 4, and drop them in. And when I tried that out, here's what I found. The position at time 0 happens to be 0. That doesn't always happen with physics stories, but it is here. So it begins right at the origin. And then the other time when the velocity is equal to 9 happens at time 4. And when I put that in, just kind of a weird quirk of the numbers, it ends up being 4 meters. Right? It's kind of odd that 0 gives you 0 and 4 gives you 4. That doesn't always happen, but it just kind of did here. Okay, the next question is asking, what is the average velocity from time 1 to time 5? Okay, so just a couple of things to notice. This is giving me this time interval, right, from t equals 1 all the way to t equals 5. So we're not going to do an instantaneous calculation. We're going to be doing just this average slope. We're going to be doing the slope of a secant line. It's not even calculus. It's kind of unimpressive. So if you want me to find that average slope, sometimes denoted like that, v with a little bar, I'm going to go and find the change in the position, right? The change in the vertical value of that position graph. So I'm going to have to do s at 5, subtract off s at 1, and then divide by how much time goes by from time 1 to time 5 seconds. So 5 minus 1, clearly 4 seconds. Okay, so this average velocity, I have to go to this position machine, right, that we had right here. I have to go there and drop in these times. Oops, there we go, clean that up. I have to go and drop these times in and see what I get. I think I've messed something up here a little bit. Give me 1 second. There we go, all cleaned up. The position at time 5 ends up being 20, and the position at time 1 ends up being 4. And we've got 4 seconds to make that 16 meters happen. So when we divide, the average velocity ends up being positive 4 meters per second. Next question, what is the displacement over the time interval from 0 to 5? All right, well, if you want displacement, that means change in position. So you're asking me to go and find out how much did that position, which we call s, change. So I'm going to have to do s at the later time, like s at time 2, and then subtract off s at time 1. So I'm going to have to do s at 5, your position at 5, minus your position at 0. The position at time 5 is 20. You can just evaluate that function we've got, or you can look at the graph that we were first given. And the position at time 0 we've already seen as 0. So the displacement is 20 meters. All right, next thing. When does the object have 0 acceleration? Okay, well, no problem. I've got this machine that tells me the acceleration at any time. It's actually equal to 6t minus 12. And what I'm wondering is, hey, are you ever 0, right? That's kind of what I'm wondering. Well, that's pretty easy to solve, right? That would be when 6t is equal to 12. Oh, yeah, okay, at time 2 seconds, you're going to have 0 acceleration. The thing will very, very, very briefly be coasting. Now, last word here, distance. We haven't brought that up yet. You have to be so careful with this, and if you've taken Physics 11, you've probably seen this issue. There's a difference between distance and displacement. Distance is the total amount of land that you've covered. And I'm just going to go back and look at this graph here for a minute that we were first given. And what you can see from this graph is for the first second we're moving forward, the position grows. Then we retreat. We actually retreat right back to where we started, back to position 0. Right, so we get up to position 4, back to 0, and then we get all the way up to position 20 there in the end. So we're definitely covering a lot of ground, but we did a little backtracking at the beginning. And this question about distance deals with backtracking. Not every object backtracks, but this one definitely does. So what I would do is pick up on the places where you know it's stopped, right, and check the endpoints. So at the very beginning, the first endpoint, we're at location 0 meters. And then looking at the graph, right, we've already seen this because we checked out when this thing stopped, but it's going to be stopped at time 1 and then stopped again at time 3, right? We found that in part E of the question. So now that you've done that in part E, we can use that information and say, okay, maybe I don't always have that graph to stare at, but I've done the math to know that it stopped at time 1 and it was located at position 4. And then the next time that it stopped is at time 3, and at that spot it's back at 0. You can just do that by evaluating that position function, and then finally at the end of the day, 5 seconds down the road, that's when this story is over, you're at location 20 meters. So you go forward 4, back 4, and then forward 20. And so distance is a bit of a tricky thing. You have to look at these little shifts and say, hey, how much have you worn out your shoes, right, as you're walking forwards and backwards? And you're going to wear your shoes out whether you're walking forward or backward. So we got 4 meters backwards, and then 20 for a grand total of 28 meters. So distance can be a bit tricky if the thing backtracks, but we can always go and find out when it's backtracking just by looking at the velocity function and then saying, okay, hey, when are you equal to 0? That's when you might start backtracking. All right, so let's take another look at the actual pictures in the story here. So we've got the position function that we were given, we found the velocity, we found the acceleration, and I just want to make sure that we're comfortable looking at this and saying, okay, how is this going to work if we're trying to just look at it as a picture point of view to figure out where things are happening on the graph. So with this first graph here, we've got position versus time, and I can see what it's doing as it goes forwards and back and then forwards again. And you have to be able to make comments about velocity, even though you might only have just this position graph. And then down below is actually a graph of the velocity, right? It's just that velocity function, 3t squared minus 12t plus 9. And we also need to be ready to look at a graph like this and say, okay, yeah, we can go and talk about velocity. So if it's a velocity graph, let's start at the bottom here first. This is really easy. People ask you questions about, hey, what's the velocity? Well, if you want to get velocity information from a velocity graph, I mean, what could be nicer? So velocity is it okay if I just say this? How about I say it's the y value, right? It's the up and down value. I know there are no y's on this graph, but it's the vertical value of a VT graph. In other words, you just rate it off. You're just like, yeah, okay, great. There it is. Peel it right off. And so I would literally just be, here's my eyeball, right? I would just be staring at these velocity values and saying, okay, hey, where are you on this vertical axis? What's going on? Oh, are you 0 or are you negative? And I would just peel the numbers off right off that vertical axis. And so here's what I notice, that there's a time in here, right here, where the graph is in the positives. Now I know it's got a downward slope. Let's not worry about that. That's actually acceleration. I'm just noticing that for the first little while, this graph is all graphed this high, right? Up above that time axis. So I've actually got in here positive y values. So I know that up here, for that first second, that velocity is positive. And then there's this time period where the velocity goes into the negatives. So all in here, I can see that the velocity graph is hanging down. Its y values are negative. So for this section of time, yeah, the velocity is a negative. And then later on in the day, we go back to positive y values. Now, again, I want to just clarify, I'm not looking at the slope of this graph. I'm literally just peeling off y values and saying, when are you above or when are you below 0? When are you above or when are you below this line, like right there, right, where velocity would equal 0? And for this section of the deal, we are up above that velocity equals 0 line. So we could say, oh yeah, the velocity is positive again. And if people were like, well, when is it 0? Well, just peel off a y value, like right here and right there. So that's the easiest deal. If they ask you about velocity and they give you a velocity graph. Now, if they say, oh yeah, the velocity is positive, okay, then words that can go with this. Yeah, here you're moving forward. Here you're moving backward because your velocity is negative. And then here you're moving forward again. Okay, well, let's challenge ourselves and let's see if we can actually peel off information about velocity from the graph up above from the wrong graph. This is a position graph, right? This is not a velocity graph. It has S graphed up and down, but there's still a way that you can go and peel off information about velocity. It's just the derivative, so it's just going to be the slope of this graph. So velocity is the slope of the ST graph, that position time graph. Okay, well, let's catch a couple of moments here. I'm noticing right here instantaneously the slope is equal to 0, and right there the slope is equal to 0. If I was to draw a tangent line in, right, if I did say, hey, you know, where would a tangent line go? Well, it would have slope 0 if I drew it in. Same thing with this other point that I've got here in pink, right? Slope is also 0 here. Now I'm not looking at y values. Now I'm going to look at slope and see if I can see what's going on. And it looks like in this whole section from 0 to 1, all in there, this graph has positive slope. And then in between those two pink points that I've got there on the page, all in here, this graph is heading downhill. So here the slope is negative. Yeah, the velocity is negative. And then for the remaining part of the graph, all in here, the graph's heading uphill. So we could say, oh yeah, look, this thing has got positive slope to it. So the graph tells me that the object has got a positive velocity. So slope is velocity if you're looking at a position graph. Okay, well that's great. That's how you can get velocity information from both of those graphs. Let's flip over the page and let's try this again. But now let's see if we can talk about acceleration information from these graphs. So neither of these graphs are acceleration, right? I've got a position graph and I've got a velocity graph. Neither of them are the right graph if people are going to start peppering me with questions about acceleration. But I still can get acceleration info from them. I'll start with the easier one. Let's start with velocity. I know that acceleration is just a derivative of velocity. In other words, it's the slope of it. So I can say here, oh yeah, if you want to ask me questions about acceleration, sure. Acceleration is the slope of the VT graph. Okay, so I'm not going to look at y values. right? I'm going to look at how this graph is pitched. Is the graph like this, going up? Is it level, or is it going downhill? That's what I'm going to be watching for the next couple of seconds. And here's what I notice. There's one place where the slope is actually equal to 0, right here. Okay, so right there at that moment, the acceleration must be 0. The object must be briefly coasting. Before that moment, again, I'm not looking at y values. Instead, I'm actually looking at the slope. And I see the graph as you move from left to right is dropping the whole time. So all in here, from 0 up until just before 2, I notice that the slope is a negative. Okay, so that tells me that the acceleration is negative for that story, for that object. And then after that, out here, all along here, this graph, this velocity graph, has positive slope to it. So that tells me that the acceleration is positive for that chunk of time. Okay, well, that's all very nice, but can we actually somehow find acceleration off of a position graph? And the answer is yes, but you just have to be kind of creative with how you stare at it. We're not going to look at y values because that's position. We're not going to look at slope because that's velocity, but instead we're going to look and see which way this thing is bent. Now officially it's called concavity, and we'll talk more about that later, but let's just be real casual with our words here. And I'm going to say this. Acceleration is the flex. It's like the bend of that position time graph. Let's just call it what we usually do here, of the ST graph. Okay, so you have to think of this as a ruler. And a ruler, a little plastic ruler, when you first look at it, it's probably straight, but you could go and bend it down, or you could go and bend it up. Now, this one here, okay, no flex. This one is flexed down or bent down. I don't care about the fact that right here it's pointing up and here it's pointing down. I'm not looking at pointing. I'm not looking at slope. I'm looking at which way you're bending the thing. And this ruler here, this one is actually flexed up. It's bent up. Again, there's a time when this ruler here is pointing down and here it's pointing up. That's slope. I'm not talking about that. I'm talking about the fact that this whole ruler that I've drawn there is bent up. There's one moment where the ruler doesn't look bent at all, and that's actually right there. Okay, so there's no flex at that moment, right here. It's actually a place that we're going to call an inflection point down the road. So right there I can see that the acceleration is 0. But in this section, all through here, that looks like a ruler, a little plastic ruler that's been bent downwards. The sides have been pulled down. And so in here I've got this flex going down. That tells me that the acceleration is a negative in that section. But in the remaining section, all along here, that's a weird looking bracket. That's a do-over. All along there, this thing is flexed up. So the acceleration is positive. Don't worry about the fact that it's actually pointing down here and pointing up here. We're not worried about that at all. We're worried about which way this thing is bent. And all through there, that thing is actually bent up. Okay, I think we've got a little follow-up question here down at the bottom of the page. When does the object change direction? Okay, so to change direction, just again, we're just practicing translating words from English into calculus. If you're going to change direction, then the velocity has to change sign. So we're talking about, is it positive or is it negative? And it has to switch. It can't just be 0. You can't say, oh, that's easy. Just find out when the velocity is 0. Well, it might actually stop, go to 0 velocity, then it might continue on in the same direction. It has to switch. And so what I do notice as I look at, I'm going to try to gather information about velocity right now. So I'll look at the velocity graph. And I can see that right here we go from being a positive velocity. We are up above, v equals 0. And then we go into negative velocity. Now, I'm not looking at the slope of this, right? That would be acceleration. And then here, I can see the graph goes from negative velocity through velocity equals 0, through that time axis, up until a positive velocity. So my answer to this would be at t is equal to 1 and at t is equal to 3 seconds. And if they said, justify your answer, I would say, look, before time 1, the velocity was positive, and after it's negative. That's how I know it's changing its direction. When is the object moving forward? Okay, we've already answered this question, but we can actually see it right here. So I'm just going to make a big mess of this graph. If you're moving forward, then that means you've got a positive velocity. I could look at either graph. Maybe I'll just look at this easy one for me down here. I'm going to look at the velocity graph. If I want to talk about velocity, this is the easiest place to look. All in here, that graph is in the positives for velocity. Yeah, I know it's got a negative slope. I'm not talking about acceleration right now. It's got a positive velocity, and then here it's got a positive velocity. So my answer to this would be, how about these times? How about from 0 up until just before 1? It's not actually moving forward at 1, it's stopped. And then after 3, it stopped at 3. After 3, all the way up to and including 5. Just trying to figure out when that velocity is positive. Okay, we're just going to do one more page here. I've got a third question though. How can you find the time when the maximum position occurs? Okay, when you're as far, to the right of the origin as possible. And my little follow-up point there is this can be great for finding the maximum height of a rock that's been thrown upwards. So I want to think about that for a minute. Let's just draw a little person here and say, okay, they're going to throw a rock, and the rock's going to go, and it's going to hit that maximum height, and then it's going to come down. And we want to try to catch this moment right up there at the top. Right? So what is it that's special about that moment? How can we find that location? Right? That would be when the S is equal to some sort of maximum position up from the ground. Well, at that maximum position, we're going to have the velocity hit 0, and it's going to go from positive to negative. So that could be a nice, easy way to catch this, right? At maximum position, the velocity, otherwise known as S prime, changes from positive to negative. Let me write that out a little better instead of that. So when does the velocity go from positive to negative? Right? You can just go and take a look and see when this happens. Oh. Sorry, just jumped a few pages here. Let's go back. Okay, so looking at this velocity graph, I want to know, when does the graph go from positive to negative? Looks to me like that's happening right there. I wouldn't want to catch this moment. If you just say, oh, it's going to be when the velocity is 0. Well, that's actually going to be a minimum in position, right? Because you're going to go backwards, and then forwards. So we don't want that moment. So we definitely want to consider looking at time 1. And then I would also just think about the endpoints, right? Those could be interesting moments too, to see if those are kind of maximums in position. And so I'm definitely suspicious of time 1. But I also want to think about time 0 and time 5. Let's go back to just where we're looking here. So we're going to consider t equals 1, but we're also going to just check out the endpoints. So I'm just going to put in here, also check. And this issue of checking endpoints, we're going to be doing this kind of thing throughout the entire course. So if you're looking at it going, whoa, what's going on with that? Don't worry, you're going to get so good at checking out endpoints. It's not a problem. So those could be some nice, interesting little maximums that we might want to go and check. So let's go and actually look back now at the position graph, see what it says. So here's what you can see. We don't really want to worry about that first endpoint, because you actually begin the story with positive velocity, and your position grows until you get to this place right here. That's definitely a maximum in position. You get up to position 4, and then you start backtracking. Then we have this minimum in position at time 3. We don't want that point. They didn't ask for a minimum. They wanted a maximum. But then you go forward again, and the calculus is not going to find this maximum in position of 20 at the very end, because it's just going to highlight flat spots for you. So we might have to go and check the endpoints and say, well, you know, if you really want to know when you're the farthest from the origin, yeah, sure, that 4 right here was interesting, but the 20 is even better. So they're both maximums, but one is the absolute maximum, right? Some little phrasing that we'll say. So what did they say? What is the maximum position? Well, you know, there's definitely 1 at t is equal to 1, and at that spot, the position was equal to 4. And it's also interesting to check out time 5. The position's even better. It's at 20. So both of those are some little local maximums, and 20 is the very, very best one. Okay, one more little bit of theory. Let's throw another physics word in here, speed. Here is the calculus definition of speed. All you do is you take your velocity and you remove any negative signs. So we're just going to put some absolute value bars on that. And all of a sudden you've got velocity. Example 2 says, hey, sketch the speed of the object. This is the same object from example 1 on the same grid as the velocity. So I can see the velocity there. That's all great. And now what I want to do is graph right on here the absolute value of that. Well, when things are positive, then the absolute value is not going to do much until you get to here. But then the absolute value of this graph will not let it go into the negatives. So it's actually going to do a little bump up and down like that. And then we're back to just taking the absolute value of a graph that was already positive. So in red, we've actually got the speed. And in blue, at least on my file here, that would have been the velocity. So the velocity can be negative, but the speed can never be. Part A, when is the speed of the object increasing? Okay, so as you move from left to right, looking on this graph, when does the thing look like the speed is increasing? If you just asked, well, when is the velocity increasing, you'd get the wrong answer, because the velocity is increasing all after 2 seconds, like all in here, the velocity is going up. It gets higher and higher as you move from left to right, but that's not what they asked for. They said, when is the speed increasing? So when is this graph in red going up? Well, yeah, here's true. That's fine. But the other time is actually here. The speed's increasing. Kind of an interesting thing, right? We're going faster and faster backwards at that point. So if I was giving my answer for this, I would say I've got a couple of times for you. From time 1 to 2, and from time 3 to 5. Don't worry too much about whether they should be square brackets or round brackets. We're going to talk more about that later. When is the speed the greatest? Well, just looking at that red graph, when is it actually going to be the tallest value ever? It looks like it's at 5 seconds. Last one, example 3. Here is a graph of everything, position, velocity, and acceleration, but somebody forgot to label which one was which, and you have to try to figure out, well, which graph is what? Okay, so one of those is position, one of them is velocity, and one of them is acceleration. Here's the kind of thing that I look for. I look for places where, like I notice one right here, this graph is flat. So that graph has a slope that's 0 right there. And this graph seems to be documenting that by having a y value that's 0. So I'm very suspicious that this graph here is the derivative of that graph there, because it seems to be nicely documenting that the upper graph was flat. Looking for a couple more of those moments. I'm just going to grab some different colors here. Here's one. This graph is flat. And this graph seems to be documenting that with a y value that's 0. Okay, interesting. Any other places that are like that? I can see that this graph is flat right here, but nobody seems to be documenting that. So that's odd. Let's keep looking. What about this spot? This graph is flat, and this one is documenting that it's 0. Okay. Oh, yeah, here's another one. This graph is flat, and that one is documenting that it's 0. And maybe one more. This graph is flat, documenting that it's 0. So the one that sort of records, hey, look, I saw you were flat, and I'll record a 0, that's going to be a derivative. So I might just pick like random letters of the alphabet and do this kind of thing. I might look at this first two little pair of points here that were in red, and I might say, well, if I take the derivative of this one, I seem to be getting that one. So I'll just pick some random letters. It's kind of like you're W, and you must be W prime. You must be one derivative down the road. Any other things that I can find here? Oh, like this one. This one seems to be 0. Derivative is 0, and this one seems to be documenting that. So maybe I could say, hey, you must be like Q, and you must be Q prime, right? And if you play that game enough, then you can figure out which one is the original graph, which one is the position, and then the other ones are just derivatives of that. So this one is I think the original. Q is the derivative of that, and then there's Q prime, the derivative of the Q. So if that's right, then this one would be position. Let's check this here in a second. This one would be velocity, and this one would be acceleration. And we don't have a graph after acceleration shown here, so that's why we don't see anybody documenting this flat spot on the acceleration graph. Okay, so is this right? Position is here. When the position is flat, the velocity would be 0. Yeah, velocity is showing that. Here, the slope of the position graph is positive. Velocities are positive here in the positive y values. Yeah, that works out great. And now if this is the velocity graph, here it's flat, and there's the acceleration graph saying, yep, okay, I'm going to document that. Okay, so I'm the derivative of u, right? A is the derivative of v. Another thing to notice is the graphs, at least with polynomials, tend to get simpler. They tend to have less bumps on them as you go up in derivatives. So the position graph seems to have 1, 2, 3 bumps to it. And then the next one down in terms of derivatives is velocity. It's got 1, 2 only, not 3, but 2. And then acceleration just has 1 bump to it. That's a characteristic that's very common to see with polynomials. And that's going to finish up our work with physics. Next time we're going to take a look at working with trigonometry.